Welcome to part 3 of this week's online lecture. In part 3 we will continue our discussion of polyatomic molecules. In particular, now that we know how to classify them, what will their rotational spectra look like? Let's start with linear polyatomic molecules. In fact, we have already solved the rotational problem for linear systems. The solution is the same as for the diatomics. It doesn't matter how many atoms you have in a line, the rotational spectrum will look the same. The characteristics of this type of molecule in terms of the moments of inertia are identical. One of the moments of inertia is 0 and the other two are the same. This means that the rotational energy levels for the linear polyatomic system are going to be identical to the diatomic molecules. We solved the Schrödinger equation for a linear system. We did this for a diatomic, but the answer would have been the same for any linear system, and so if we ignore the centrifugal distortion term, then the rotational term, or energy, will be given by this familiar expression, where I've written it down in terms of the rotational constant in wave numbers. And the rotational constant, as you can see, is inversely proportional to the moment of inertia. Now this moment of inertia here is associated with the B and C axes, and of course they are the same. You cannot distinguish between them. The difference, though, between, say, a triatomic linear molecule and a diatomic linear molecule is that the triatomic molecules are larger. This means that their moments of inertia are also going to be greater. Remember, the moment of inertia is just the sum of the masses times the distance from the centre of mass squared. The more atoms you have in a line, the greater will be your moment of inertia. So what does this mean? If our moment of inertia is larger, it means that my rotational constant is going to be smaller. And remember, the spectral lines are approximately 2b apart. So that means that the spectral lines for polyatomic systems are going to be much closer together than they were for the diatomic system. And we can rationalize that in exactly the same way as we did for the diatomic systems when we were talking about the effect of centrifugal distortion. Because the spacing of the energy levels is related to the size of the molecule. This is exactly the same as when we discussed the particle in the box system. The larger the box, the closer the energy levels. In this system, the rotational wave function can spread over a much larger region, and so the energies are going to be smaller and the energy levels are going to be closer together. Let's have a look then at a triatomic system, and this is rather an interesting one. This is the OCS, or carbonyl sulfide molecule. So this molecule has an oxygen atom, a carbon atom and a sulfur atom all in a line. The sulfur atom is of course a lot heavier than the carbon and oxygen atoms, and so the centre of mass will lie somewhere along the CS bond. And we can define therefore the distance the carbon atom is away from the centre of mass as r sub c. The distance the oxygen atom is away from the centre of mass is r sub o, and the distance the sulfur atom is away from the centre of mass is r sub s. We've got a condition that enables us to identify the centre of mass. If we take the product of the mass of the oxygen and the distance it is away from the centre of mass, and sum that to the mass of the carbon times the distance the carbon is away from the centre of mass, it will equal the mass of the sulfur times the distance the sulfur is away from the centre of mass according to this equation. Of course, in terms of saying something about the structure of the molecule, we are not really interested in what the distances are away from the centre of mass. We want to know what the bond lengths are. We want to know what the CS bond length is. But of course, we can define those in terms of these distances. Notice that the CO bond length is just the RO distance minus the RC distance. Similarly, CS bond length is simply the RC distance plus the RS distance. We can calculate the moment of inertia around the centre of mass through which the rotational axis will be going in exactly the same way as we did for the diatomic system. So it is just the mass of the oxygen times the distance from the centre of mass squared plus the mass of the carbon times the distance from the centre of mass squared, and the same for the sulfur atom. We can then use these constraints on our system, this one associated with the moments around the centre of mass, and this enables us to transform the distances from the centre of mass to bond lengths. And we can convert this equation into this one. The mathematics is a bit tedious and I'll never ask you to do that. What about the bond lengths of OCS then? Can we determine the CO bond length and the CS bond length from a calculation of the rotational constant B? Well, yes we can, but it's not obvious. If we only had the value for B for this isotopic mass of OCS, we couldn't do it. This O16C12S32 has a rotational constant of 0.202864 wave numbers. But the moment of inertia has two unknowns in it, the two bond lengths. So we can't solve the system from one value of B. We need two values of B. Well, we can get the second value for B for this system if we substitute for a different isotope of sulfur. In this case, sulfur 34. Because it has a different mass, it will have a different moment of inertia, and so a different value of B. This time, the value of B is 0.197910 wave numbers. But the thing that we know is that the bond length or structure of the molecule itself won't be different when we make this isotopic substitution. The bond lengths do not depend on the masses of the atoms in just the same way as we discussed with the diatomics. If we get a second rotational constant, we'll have two rotational constants, so we can set up two equations in which we have two unknowns and we can solve them simultaneously. In this particular problem it is not very easy, but if you do that, you would come up with these two values for the bond lengths. So the CO bond length is shorter, as you would imagine, than the CS bond length. Let's have a look at our spherical top molecules. We of course have this condition, that the moment of inertia around the A-axis is the same as the moment of inertia around the B-axis, is the same around the C-axis. The moment of inertia is independent of the choice of axes. The other thing we know about the spherical top molecule is that there is no permanent dipole moment in the spherical top molecule. Symmetry tells us that. So it doesn't have a microwave spectrum. So in essence, we don't have to worry about this classification of molecules. But just as we discussed for homonuclear diatomics, it doesn't mean that the molecule doesn't possess rotational levels. It has rotational levels, and indeed it can change its rotational energy through collisions, for instance. It cannot change its rotational levels through interaction with light. Or can it? Here is a spectrum for silicon tetrahydride, SiH4. This is the rotational spectrum. These numbers, these intensities, are incredibly small, but this is unambiguously a rotational spectrum for a symmetric top molecule. One of the things you want to notice about this spectrum is the size of the J value. The spectral line with maximum intensity is for the transition from J equals 15 to J equals 16, and as we go to lower values of J, the intensities are dropping off. So the question is, how on earth can we see a rotational spectrum for silicon tetrahydride when it doesn't have a permanent dipole moment? How was this possible? Well, we can appreciate it in terms of symmetry again. We can understand what is going on. If we increase the rotational energy of the system, as we go to higher and higher rotational energy levels, the J becomes larger and larger, the molecule is rotating faster and faster. Centrifugal distortion is going to modify the shape of this molecule. You can imagine that if we rotate the molecule around the C3 axis, the off-axis hydrogen atoms will rise ever so slightly towards the horizontal plane perpendicular to the C3 axis. This will be a tiny effect, but this distortion can introduce a dipole moment to the molecule. Look at the conditions that had to be used in order to see that spectrum. The path length was over 10 meters, the pressure was over 4 atmospheres, and they also had to do it with a Michelson interferometer. But it arises because of centrifugal distortion as you rotate faster and faster, so you can see a weak microwave spectrum. It is possible for tetrahedral molecules. You wouldn't, however, have seen it for an octahedral molecule. If you rotate that kind of molecule around a C4 axis faster and faster, it doesn't generate a dipole moment, but it will for a tetrahedral molecule like methane or silicon tetrahydride. Now I want to talk about symmetric top molecules, and as we've discussed, we've got two different types. We've got the prolate and the oblate. Now it is possible that our symmetric top doesn't have a dipole moment. However, if it does have a dipole moment, it will have a rotational spectrum. So we'll start off with prolate symmetric tops, where the moment of inertia around one of the axes is smaller than the moments of inertia around the other two axes. For phosphorus oxychloride here, the A-axis is aligned along the PO bond. The moment of inertia is smallest around this axis. You can't determine that just by looking at it. You have to calculate the moments of inertia. The moments of inertia which are perpendicular to this axis will be the same. The reason why we call it prolate is because if you were to map the rotational constant in space, then it would have this kind of rugby ball shape. I'm going to let you think about that and see whether that makes sense. This is benzene, and this is an oblate molecule. The moment of inertia around the C-axis is larger than that around the A and B axes. In fact, it is twice the size of the moments of inertia around the B and A axes. Now for this benzene system, of course, you won't see a rotational spectrum because it doesn't have a dipole moment. But the reason it's called oblate is that if you map out its rotational constant in space, then it would have this kind of flattened M&M shape to it. Let's have a look then at the prolate symmetric top in a little more detail. In the following discussion, I'm not going to include centrifugal distortion. Well, what's changed? Now, when we solve the Schrödinger equation for the rotational problem for the prolate top, we get the term B times J into J plus 1 here. This is the familiar term that we get for diatomic and linear polyatomic molecules, but notice that we also get this additional term here. This new term also involves the rotational constant B, but it also includes the rotational constant A. Now the rotational constant B is called B because it is associated with rotation around the B axis. The rotational constant A is labelled A because it is associated with rotation around the A axis, and it won't surprise you that there will also be a rotational constant C which is associated with rotation around the C axis. For prolate tops, of course, the moments of inertia around the B and C axes are the same, and so this equation that describes the energy levels of the system doesn't involve the C rotational constant. So the energy levels do depend on this A parameter, the rotational constant around the A axis. But note that it also depends on this K quantum number here. I'll discuss where this K quantum number comes from in a bit more detail a little later. So the additional term depends on the difference between the A and B rotational constants times the K quantum number squared. So just to remind you, when we were discussing the linear diatomics, we introduced the J and MJ quantum numbers. You'll remember that the J quantum number is equal to 0 or a positive integer. Remember the MJ quantum number is associated with the spatial quantization of the molecules, and that was the projection of the angular momentum on a laboratory fixed axis. Note that again, just like for the linear molecules, the energy of the rotational state does not depend on the MJ quantum number. The MJ quantum number does not appear in this energy expression. The K quantum number comes from the projection of the angular momentum on the principal axis of the molecule, in this case the A axis. Now why does this occur? We can justify that in a manner similar to before. Remember that I said that the quantum numbers come out of the solution of the Schrödinger equation whenever you have to apply a boundary condition. Now when you've got two rotational axes, you have to have two coordinates, and so you have two boundary conditions that arise from these two coordinates in order to satisfy the single valuedness of the wave function, and so we have two quantum numbers to worry about. This system will also have the J quantum number and the MJ quantum number, but we're going to have a third quantum number K that comes about because now we've got three rotational axes. We have three quantum numbers to worry about. We have three boundary conditions which are going to be enforced when solving the Schrödinger equation, and so therefore we get the third quantum number arising naturally. It has to be said that there isn't a unique choice of how we define these quantum numbers. This choice is the one that makes the most sense because it makes the energy equation look the simplest. But in terms of the results, you could solve this with a different definition of these three quantum numbers and a different energy expression would arise, but if you calculated the energy levels they would have the same numerical result. This is the set of quantum numbers which give us the simplest energy expression. The K quantum number is also restrictive. Remember that for the MJ quantum number its values were restricted by the value of J, which identifies the rotational energy level you were in. Similarly, the K quantum number is restricted by the rotational energy level that the molecule is in. So the values of J can be, as before, 0, 1, 2, 3, etc. But if J is equal to 3, then the possible values of K would be 0, plus or minus 1, plus or minus 2, and plus or minus 3. And in a more general form it will be 0, plus or minus 1, plus or minus 2, all the way up to plus or minus J. So you've got 2J plus 1K quantum numbers associated with any value of J, just like the MJ quantum number. and these quantum numbers come from the projection of the angular momentum on the a-axis, and I'll illustrate that shortly. Well, notice this expression up here was in joules. We can of course convert this to wave numbers by simply dividing this expression through by hc tilde, where c tilde is the speed of light in centimeters per second. Remember that tilde signifies that I'm using centimeters rather than meters. So the rotational constant is as before, but on the moment of inertia I've put this little b subscript here. This is because the moment of inertia is around the b-axis, and on the a rotational constant I put a little subscript a on the moment of inertia to indicate it is around the a-axis. Let's have a look to see if there is any difference for the oblate symmetric top. Well, not very much. The solution from the Schrödinger equation has changed slightly. For the prolate, this additional term over here was of course a minus c times k squared, but now for the oblate it is b minus c times k squared. Notice that the term in brackets is overall positive because c is going to be smaller than b, just like a is larger than b. Remember that the rotational constants are inversely proportional to the moment of inertia. Again, j can have values of 0, 1, 2, etc. And k can have values of 0 to plus or minus j. And remember, the k quantum number arises from the projection of the angular momentum onto the c-axis. And if we divide this expression for the energy up here that is in joules by hc tilde, we can express the energy of the rotational levels in terms of wave numbers, which I've reproduced here. So the big difference now is that when we were discussing the diatomic and also the linear polyatomics, the energy term only depended on the j quantum number. This time, not only does it depend on the j quantum number, it also depends on the k quantum number. To give you a feel then for what I was saying in terms of the k quantum number, here are two relatively extreme results in terms of rotation. This molecule is a cylinder. It has moments of inertia around all three axes. So it is a three-dimensional object which is spinning in space, and we can spin it around a variety of different axes. This vector here is my angular momentum vector j. So my cylinder is rotating around this axis, and it is almost parallel with the molecule's principal axis. So that when I project my j vector onto the principal axis, I get my k quantum number. And my k quantum number in this case is going to be pretty much equal to j. However, if I'm rotating my molecule perpendicular to the principal axis, then the projection of this onto my principal axis will be 0, and so k will be 0. You can see that k will go from being positive j all the way through 0 to negative k. So that is where the values of k are coming from. So in this case we have three quantum numbers arising for a symmetric top, and they are j, k and mj. And they arise because we are solving boundary conditions associated with each degree of freedom of the molecule. Let's return to our rotational term for the symmetric top, and we will only consider the prolate top, but an analogous expression exists for the oblate of course. Here is the rotational term. If we know our value of B and we know our value of A, we can calculate the rotational energy levels. If we know what the molecule looks like, we can calculate the rotational constants ourselves and therefore predict what the energy levels are for this system. And below, that is what we have done for all the rotational levels which have j equals 0 or j equals 1 quantum numbers. If j equals 0, our only possible values of k are 0. So if you substitute those values into our energy expression, our energy is equal to 0. However, if j is equal to 1, then k could be equal to 0, as it is here, in which case the energy will be equal to 2b, or it could also have values of k is equal to plus or minus 1. And notice that their energies are degenerate because the energy depends on k squared and not on k. Because it depends on k squared, it doesn't matter if k is positive or negative, its effect on energy will be the same. and so therefore when K is not equal to 0 we have doubly degenerate energy levels arising, and we know that degeneracy will modify our rotational spectrum slightly in terms of the intensities of our spectral lines. Well, what do the different signs of K refer to? The signs of the K quantum number arise because the molecule could be rotating clockwise or anti-clockwise. Of course, if the rotational axis is perpendicular to the principal axis, as we have here, then both pictures are describing the same rotation. Now for the degeneracy of the rotational levels, when K is equal to 0, I will have 2J plus 1 degenerate levels. That 2J plus 1 is coming from the fact that MJ can go from minus J to J. But if K is not equal to 0, then I will have twice as many degenerate levels, because for every set of possible MJ values, I've also got this double degeneracy from the fact that the energy level associated with plus K will be the same as that associated with minus K. All levels with K greater than 0 have this additional double degeneracy. So let's try to predict the rotational spectrum for a symmetric top. We'll do it for the prolate top again. There are analogous expressions for the oblate top. Remember, we have an expression for the rotational energy of a symmetric top in terms of the two quantum numbers J and K. But remember that spectroscopy is about the transition from one energy level to another energy level. So what we want to calculate now is the difference between any two energy levels. The specific selection rule with regard to the J quantum number still applies, that is, that delta J is equal to plus or minus 1. But is there a specific selection rule associated with K? And the answer is yes. The specific selection rule associated with K is that delta K, the change in K, must be equal to 0. And as you know, there is also a selection rule associated with MJ, but of course the energy doesn't depend on MJ, so it is not going to affect our spectrum. Because our energy depends on K, the selection rule associated with K could possibly affect our spectrum. So let's calculate the frequency for the transition from J to J plus 1, noting of course that the K quantum number will not change. So we can calculate the rotational term when the system has the J plus 1 and K quantum numbers, and take away the rotational term when the system has the J and K quantum numbers. This difference will correspond to the frequency of the spectral line, and we find that it's equal to 2b into J plus 1. So note that the frequency of a spectral line does not depend on the K quantum number, and the reason why is that the terms involving the K quantum number cancel each other out when we calculate this difference. This means that the spectral lines occur at exactly the same frequencies in terms of the B rotational constant that we had for the linear systems, so despite all that effort, it hasn't modified the spectrum of our molecule. The frequency of the spectral lines still occur at 2b into J plus 1, which means the spectral lines are still, for a rigid system at least, 2b apart, just like they were for the linear systems. So that means essentially that the spectrum is independent of the K quantum number. This seems like a great thing, it simplifies what the spectrum looks like. However, if it had depended on K, we could have gotten information about the moment of inertia around the A-axis, which would have given us a lot more information about the molecule. Unfortunately, we can't get any information about the A-axis and the moment of inertia around the A-axis. So it basically means that only the moment of inertia around the B-axis can be determined from the rotational spectrum of the symmetric top. So information about the A rotational axis in a prolate top cannot be determined from the rotational spectrum. We can justify this semi-classically. Remember that when we have a diatomic molecule, a heteronuclear, so that it has a permanent dipole moment, we got a rotational spectrum because the electric field of the photon could couple with the rotating dipole moment. Now if we have a prolate symmetric top like the one shown, and we rotate around the B-axis, you can see again that because the dipole moment in this molecule will be aligned along the principal axis, and that is the A-axis, rotation around the B-axis results in an oscillating dipole moment that can couple with the electric field of the photon. However, if we rotate around the A-axis, you can see that there is no oscillating dipole moment associated with it. As you rotate around the A-axis, the dipole moment is still pointing upwards and it remains unchanged. It doesn't oscillate with time. no oscillating dipole moment results, and so it cannot couple with the electric field of the photon, and so it is not surprising that the selection rule tells us that we are not going to get any information about this in the rotational spectrum. So let's compare our linear and symmetric rotor systems, ignoring centrifugal distortion. So here is the moment of inertia for the prolate symmetric top. We can modify it for the oblate if we wanted to. For the linear top, the moment of inertia around the A-axis is 0, and for the prolate top is non-zero, but it is smaller than that around the B and C axes. The energy levels for the linear top have this term, Bj into J plus 1. For the symmetric top it has the same term as for the linear molecule, but it also has this additional term here that arises because we're able to rotate around the third axis. Now for the quantum numbers that appear in the energy expressions. We can ignore the mj quantum number because it doesn't affect the energies. For the linear rotor, we have our j quantum number, and that can have values of 0, 1, 2, etc. And the same is true for the symmetric rotor. But because of the third rotational axis, we've got a third quantum number, and this one is restrictive. It can go from 0 to plus or minus j. Notice the similarity in the selection rules. For the linear system, it was just del j is equal to plus or minus 1. Same for the symmetric rotors. But we also have this additional specific selection rule for the symmetric rotor that delta k is equal to 0. But as we've just seen, it doesn't affect the spectrum. The separation between levels is just 2b into j plus 1, which means that the distance between each spectral line is equal to 2b. This is the end of part 3 of this week's online lecture. Please continue on to part 4.